Good day everyone and welcome to these lectures which we are continuing on adsorption, which is used in the as a physico-chemical process for water or wastewater treatment. So, it is one of the unit operations which is used commonly. So, in the previous lectures we started studying regarding the adsorption kinetics, and we found that how to acquire the data for adsorption kinetics in a lab using the actual wastewater and how to get the basic data with respect to time versus the adsorption capacity, and that data can be fitted to various types of kinetic models. So, the basic thing is that if any of the model is well fitted, that means all the assumptions which are there with respect to that model can be represented. Overall, the basic mechanism can be represented by that assumptions which are there for that model. Second thing is that we can use the fitted parametric values to represent the adsorption kinetic by that model, and further that whole equation can be used in the design of continuous adsorption unit also. So, this is there. So, we will continue. In the previous lecture we studied how to acquire the data. Now, we will try to analyze how to use the data for actually fitting any of the first order, second order models, etc. So, and we will be using a simple linearization approach also. Non-linear kinetics can also be used for solving. So, any of the approach can be used. So, the data which is given here, that the variation of residual concentration of one dye, which is methylene green dye, with time during its adsorption by activated carbon for initial concentration of 100 milligram per liter at 25 degree centigrade is given in this table. So, this is there. So, in the previous lecture we have already found out that we get the data only time versus CT. So, certainly the large number of beakers etc. may have been used, and they were kept in the same incubator shaker for these times which are given. Now, each of the beaker contained 100 milligram per liter of methylene green dye, and in each of the beaker adsorbent dose of 10 gram per liter has been given. So, that means here we are directly giving the value of 10 gram per liter directly adsorbent dose. So, adsorbent dose, if it is represented by m, so it will become like it is actually W by V, where W is in how much gram of how much mass has been used. So, it may be having a unit of gram, and V generally it will be 50 ml, 100 ml, something like this, but we can always convert this thing into liter. So, m is represented as the adsorbent dose in gram per liter. So, directly 10 gram per liter has been given here. Now, we have to find out the pseudo first order and pseudo second order kinetic parametric values and how to represent the model. Now, first we have to calculate use this data for calculation. So, concentration is fixed in each of the beaker, it is 100 milligram. Dose is also fixed 10 gram per liter already given. Now, the time has been given 0, 5, 15, 30, 60, 90, 120, 240 and 300 minutes, up to which the different beakers were kept in the incubator shaker at 25 degree centigrade, and after some time these were the values which were obtained. Now, what we do is that from this we can get the Q2 value, and generally these are not highly accurate, only up to a 50, 25 is enough. So, we can still determine the value from this expression which was given in the previous lecture also, C0 upon Ct W by V, and this can be can also be given as C0 minus Ct upon m, and where m is the adsorbent dose. So, this is like m. So, for the first case like 50, so we can always find out 100 minus 50. Suppose I am taking only 50, so 100 minus 50 upon 10. So, it will be around 50 by 10. So, that means around 5. So, this is what is there 4.9021. So, because it is actually equal to 51. So, this is the case. So, 51 it will be 49 divided by 10. So, that is why it is 4.9. So, this is the value. So, this way we can determine the QT. Now, there are two approaches. One approach is to find out the QE values. Generally, the last data which is there. So, because we see here the concentration is not changing much after some time. So, that means the QE value, the equilibrium value experimental is virtually 9.55 maybe. So, this will be the maximum adsorption capacity which is possible at equilibrium condition for these sets of parameters. So, this is there. Now, in the second step we have to use this data for fitting. So, already we have performed the calculation. So, what we can do is that we can use any non-linear approach for finding out the parameters of Kf. So, under that approach we can always use any of the regression techniques for solving this, and second approach is to use the linearization approach to solve. So, both any of the approach can be used. We can always linearize the first order model and second order model. We can use the non-linear approach and directly go for regression and fit using the regression fit, and in that case what we do is that we minimize the sum of square of errors. So, any of the error functions can be used. So, like this is sum of square of errors. So, that is possible SSE, and this SSE can be represented by something like this. So, QT calculated minus QT experimental divided by QT experimental, and okay. So, no, we do not, for if we divide, so it will become average of error. So, for square of error we do not divide, we can directly use this expression for finding out, and we have to sum for all the data sets from 1 to n. Similarly, there is another function which can be used, which is called average relative error. So, that function can be also be used. So, under that condition what we do is that in the average relative error it will be like this 1 by n summation I is to 1 to n, and then we can use the expression like QT calculated minus QT experimental divided by QT experimental, and we can take the mod of this. So, that the minus and any negative error and positive error do not cancel each other. So, we can find out average relative error, also called as ARE. So, we can use different types of error functions and minimize those error functions with respect to such a manner that we can find out the Kf and the calculated values of QE. So, this is possible, and we can later on use these values to again get the fitting like this. So, if we represent the data, this is QT versus time. So, it will be given by this experimental data points. Now, in the actual case we found that the actual experimental value is around 9.55, the QE values. So, it is actually wrongly written, it is 9.55. So, this is the experimental value, and as per the model fitting pseudo first order we are finding that okay, the QE calculated value is 9.44 and the Kf value is here. Now, in the second order the QE calculated value is 9.8 and the Ks is this and Hs is this. So, what we cross check is the any of the error functions SSC, which one is minimum for. So, here we can directly use any of these parametric values, or here also you can see the fits also both the models. So, pseudo first order, pseudo second order fitting is also given here. So, we can use any of these approaches to find out the values of the rate constant. Now, going further, along with the adsorption kinetics, adsorption isotherm models are also very important, and this is so because we always try to see that what is the maximum adsorption capacity which is possible, and what is the maximum adsorption capacity with respect to some equilibrium residual concentration. So, we always to find out in chemical engineering and in particular in mass transfer, we need to have some equilibrium data points, then only we can find out whether with respect to at that temperature how much will be the equilibrium data points, and then we draw operating lines and other things. So, like for Henry's law. So, as per Henry's law, it is the equilibrium data is generally linear because we consider only dilute concentration. If higher concentration is there, the curve may be like this. So, operating line will may be like this. We can decide the operating line ourselves, and based upon that we can find out the length, height, diameter etc. of the actual packed bed. So, this is possible. So, without equilibrium data we can never design a system. This is first thing. So, we require equilibrium data for any unit operation to design, and if it is mass transfer control. So, this is possible. So, we require these isotherm models which actually represent the equilibrium data at that temperature to this is there to optimize and design any adsorption system. For adsorption of adsorbate, it is important to establish the most appropriate correlation for equilibrium curve. So, this is there to optimize the design of any system. This is very important. So, various types of equations like Freundlich, Langmuir, Temkin, Redlich-Peterson, multiple more than 30 type of isotherm equations are available, and BET is also one of them. We will discuss that in detail later on. So, some of the common isotherm equations are like this: Freundlich, Langmuir, Redlich-Peterson, Temkin, and any isotherm equation is actually represented by QE, Q equilibrium. At equilibrium, what is the adsorption capacity, and it is always a function of residual concentration of the pollutant in the solution. So, all these equations are actually QE which are function of CE, and these functions which are there other parameters that we have to find out, like for Freundlich Kf 1 by n, this is 1. So, these are 2 parameter models we can see here, Freundlich, Langmuir, because they have only 2 unknowns. So, Qm and Kl. Similarly, Temkin also Bt and Kt. So, we have 2, these Freundlich, Langmuir and Temkin are 2 parameter models. Redlich-Peterson, whereas it is 3 parameter model because we have 3 terms Kr, Ar and beta. So, 3 unknowns are there. So, we can have large number of equation models, and any of these can be used to represent the adsorption isotherm or equilibrium curve data. Now, going further, because Freundlich and Langmuir are most commonly used simple 2 parameter model equations. So, we will try to discuss Freundlich and Langmuir little more. So, Freundlich isotherm gives the variation in the quantity of gas or pollutant adsorbed by a unit mass of solid adsorbent with the change in the pressure oblique concentration. So, this is there concentration of the system for a given temperature. Now, the Freundlich isotherm is derived by assuming a heterogeneous surface. So, one of the first assumption is that it assumes the adsorbent to be a heterogeneous surface. with non-uniform distribution of heat of adsorption over the surface. So, this is one of the basic assumption which is there for Freundlich isotherm, and this is represented by this expression. Exact derivation can be looked into the original paper. Now, this equation can be linearized using this approach. So, we can take log on both sides. So, ln q is equal to ln kf n into ln c. So, what does it tell? So, here the qm is the QE is the equilibrium adsorption capacity, CE is the equilibrium concentration of solution, Kf is the relative adsorption capacity Kf, okay, and n or 1 by n, we can here it will become 1 by n. 1 by n is the Freundlich constant that we need to determine. So, this is there. Now, going further, there is another model which is most commonly used, it is called Langmuir isotherm. So, Langmuir isotherm or adsorption isotherm predict linear adsorption at low adsorption densities and a maximum surface coverage at higher metal concentrations or higher solute concentration. So, it can be any of these. So, this is the assumption. Now, it is applicable for monolayer adsorption. So, in the Langmuir we assume a monolayer adsorption only. So, that means it is only applicable for chemisorption system because they have a monolayer adsorption. So, this is there. Now, this can be represented by this equation QV is equal to QM KL CE 1 plus KL CE, and this can be linearized also using this equation. The good thing is that we have CE known, we have QE known, and we can plot a CE by QE versus CE equation. In fact, this equation can be converted into many linear equations. So, this is there, and once this is known, the slope will be equal to 1 by qm and intercept will be equal to 1 by KL qm, and since qm will be known from slope, we can determine the KL value also. So, this is there. So, KL and qm are the Langmuir constants. QM is very important because it represents the maximum monolayer coverage which is possible. So, this is like a maximum adsorption capacity of any adsorbent with respect to any adsorbate. So, this we can determine. Now, how to find out or acquire the data for isotherm or equilibrium analysis. So, as we have done earlier, we will again discuss this with respect to kinetics. So, in this there is a difference. Difference is that we again take lot of beakers. Okay. So, we have many beakers which are taken, and for acquiring this data, and again since beakers are, we fix certain parameters. So, one of the fixed parameters could be temperature, suppose it is 25 degrees centigrade, and then in addition to that we again fix the adsorbent dose or mass also. So, like adsorbent dose will be fixed. So, we have two possibilities. One is that to vary the adsorbent dose and keep the concentration constant. Second approach, which is more commonly used in the experimental case, is that we vary the concentrations. So, each of the concentrations will be different. So, like starting from 10. So, if each of the 10 milligram per liter, 20, 50, 100, 200, 350 maybe, 500, everything is in milligram per liter. Now, adsorbent dose we fix, suppose 10 gram per liter. So, each will be having 10 milligram per liter. Now, there is a difference with equilibrium time. So, from the equilibrium data curve, kinetic data curve, we try to get the what is the time which will be sufficient for equilibrium to attain. So, like in the previous if we take the previous problem, we find that around 300 minute equilibrium is attached. So, we take any time more than 300 minutes. So, we can take maybe 360 minutes and we will fix the time. So, that will be equilibrium time. So, after this time, so each of the beaker will be kept for this much time in the incubator shaker at 25 degree centigrade, and after that the adsorbent will be separated out, and from the supernatant we will try to measure the residual concentration, and we determine here the residual concentration which is at equilibrium, because we have given enough time for equilibrium to attain, and we will try to find out each of the equilibrium data which is there. So, this will be like this. Actual data will look like this, that we have C0, okay, and because there is no factor of time. So, C0 will be there 10, 20, 50, 100, 200, 350, 500. Then we have residual concentration which is there. So, each of the residual concentrations will be known, okay, and after that we determine the QE. So, this is like CE, this is concentration at equilibrium, and then QE. QE can be determined as C0 minus CE, okay, upon M, or as previously we can find out is C0 minus CE W into V. So, any of the formula can be used for finding out these values. For first case, suppose the equilibrium concentration is 8. So, this will be 10 minus 8 upon 10, because we have already used 10 gram per liter. So, this will be 2 upon 10 milligram per gram, or 0.2 milligram per gram. So, similarly we can find out each, and we can draw a graph like QE versus CE. So, this is called as adsorption isotherm at 25 degree centigrade for one concentration solution. So, this is how we try to find out the graph. Now, let us try to solve some problems to better understand this. So, here a numerical is given, isotherm data is given, where the residual solution concentration versus amount adsorbed on the adsorbent QE data is given for a dye which is malachite green adsorption by activated carbon, and adsorbent dose again for simplicity has been taken as 10 gram per liter, and these are the various concentrations various residual directly equilibrium concentration, and the QE value is given. Here the in place of C0 directly this value is given. It is possible that in some of the questions only C0 versus CE data is given. So, from that data you have to calculate the QE data. So, this is there. So, here directly CE versus QE data is given. Now, we have to find out the Freundlich and Langmuir parameters using in nonlinear or linearization approach. So, suppose we have to find out for Freundlich. So, Freundlich equation already we found out. The Freundlich equation is Q is equal to Kf Ce raised to 1 by n, and its linear form is ln Qe is equal to ln Kf plus 1 by n ln C. So, this equation is there. So, we can plot a curve of ln Qe versus ln Ce. So, what we do is that we have to check that we have to determine the ln Ce and ln Qe. So, ln Qe will be on the y axis, and then ln Ce will be on the x axis, and we can plot this, and from the plot the slope will be equal to, from the equation the slope will be equal to 1 by n, and the intercept will be equal to ln Kf. So, both we can determine. So, this is what is done. Ce Qe is known. So, we determine ln CE, ln QE, all the parameters are determined here. Now, we plot this by these points, you can see here all these points are there, and we fit a equation on these points. So, this equation is given by this, the r square value is 0.9927. So, fitting is good, and we can use, so the intercept is 0. The slope is 0.4111 and the intercept is 0.1732. So, we can see here. So, slope is equal to 1 by n 0.411 and intercept is this. So, from this we can find out the kf value. So, through this we can find out the both the parameters kf and 1 by n. Similarly, we can find out there is another equation which is given here. Here in place of directly given the CE versus final data, here initial concentration is given, dose is 5 gram per liter and final concentration which has been found is given here, and the dose is 5 gram per liter. So, we have difference, we have in place of directly getting the CE versus QE data, we have the initial concentration, that means C0 versus C data is available here. Now, what we can do is we have to find out the Langmuir and Freundlich parameters for this afloxacin adsorption by biochar. So, if we find out, so initial concentration is there and this dose is there, Q final or C is given. So, we can find out this QV is equal to C0 minus C upon dose, or we can call it M. Okay, so, the adsorbent dose is like M. So, QV has been found out, C is already known. So, what we do is ln QV, ln C we determine, and similarly we can determine C by QV also, because we will use this column, okay, versus this column for finding out Langmuir parameters, and these two columns will be used for finding out Freundlich parameters. So, we can perform the calculation directly. So, from here if you plot ln QV versus ln CE, the slope will be 0.2121 and intercept is 0.15056. So, Kf and n can be found out, or 1 by n can also be found out, which will be equal to 1 by 471476. So, these number of digits are not essential, we can only keep up to a certain 4.50 is enough, the parametric value of 4.7 value. So, we can always reduce to significant digits, only for calculation sake it is given here. Okay. Now, similarly we can plot the C by QE versus CE data. So, that here C by QE versus CE data, and we can, here you can see here the plotting has been done, they have been linearized. So, slope is 0.0583 and intercept is given. So, once this is there, for Langmuir equation of this type, we know the slope is equal to 1 by QM and intercept is equal to 1 by KLQM. So, this slope is, for this case, this slope is equal to 1 by QM and this is intercept is equal to 1 by KLQM. So, QM we can take 1 divided by 0.0583. So, this will be the answer, and once QM is known and intercept is known, we can determine the KL value. So, through these equations we can find out different parameters, and then we can start using this equation. So, we can represent the data. What we have to do is that we should cross check what is the value of R square. So, we can see here the R square is better for Langmuir isotherm. So, that means for this afloxacin removal case, we should use the equation this QV is equal to QM KLC 1 plus KLC, this expression, and we can put these values in this equation, and whatever is the final equation as a function of C, we can represent this data by this Langmuir equation. and this Langmuir, this data can be later on be used for plotting the equilibrium data on the curve, or it can be used for designing the system later on. So, that we will study later. So, these are Langmuir and Freundlich isotherms are the most common isotherms, and in today's lecture we try to understand how they can be determined. So, through this we will end this lecture. In the next lecture we will try to understand another important isotherm equation which is called as BET equation, Bronner-Emmett-Taylor, and that isotherm equation can be used in one of the apparatuses to find out the actual porosity parameters. So, different surface area, pore size, all those things can be determined using the BET equation, using the nitrogen adsorption data. So, this is there. So, we will continue further in the next lecture. Thank you very much.